The challenges of condition-based maintenance. An effective condition-based maintenance regime requires a good understanding of asset criticality, failure rates, modes and effects, as well as total cost of failures. Often, organizations install major assets with very little consideration given to maintenance, operations, and support. This practice is expensive because the costs of maintenance, operation, and support constitute a major portion of the asset lifecycle costs. A study by the commercial airline industry revealed that only 11% of components demonstrated failure characteristics that supported a scheduled overhaul or replacement, time-based maintenance. The remaining 89% exhibited random failure characteristics. However, many maintenance organizations continue to perform intrusive time-based maintenance. The airline study led to the development of condition monitoring technologies and reliability-centered maintenance. Condition-based maintenance, CBM, if technically feasible and economically justifiable, reduces maintenance costs and improves asset reliability. CBM requires the installation of monitoring devices on subsystems or parts of an asset to measure degradation. Whenever the monitor detects degradation, a report could be transmitted to a computerized maintenance management system, CMMS, which could issue a work order. The costs and benefits of remote monitoring should be compared to the cost and benefit of frequent and infrequent maintenance inspections. Understanding what to monitor for a given asset requires reliability and financial related data. CBM should be based on asset criticality, safety, environmental and operational impact, and cost, failure rates. A number of techniques such as failure modes, effects, and criticality analysis, FMEA, and reliability-centered maintenance, RCM, which are components of integrated logistics support, ILS, have been used to identify and select cost-effective maintenance strategies. A CBM regime and standby units such as protective devices or infrequently used assets would not be effective since upon startup hidden failures could occur. However, to counteract hidden failures, fault finding FF tasks could be performed to check the state of assets or items with dormant function. A typical example is an emergency generator that is generally idle until needed. FMEA is a systematic approach for identifying all possible ways that an element within a system can fail, as well as the causes of each failure and effect. Consistent use of failure mode effect analysis in the design process enables engineers to design out failures and produce reliable, safe assets. Sensors capable of detecting pre-failure signals can provide alerts and alarms notifying the asset operator of the potential of impending failure. Reliability-centered maintenance follows failure mode effect and analysis. It is a systematic approach in identifying the most applicable and cost-effective maintenance task for an asset's elements, services, and equipment from a rigorous analysis of consequences of failure. In order to apply reliability-centered maintenance, the organization needs to fully understand the functions of physical assets and the nature of failure related to these assets. When purchasing critical asset, the statement of work should specify that the suppliers perform failure mode and effects analysis and reliability-centered maintenance analysis, as well as recommend strategies to minimize maintenance costs through the implementation of condition-based maintenance or other effective maintenance regime. Moreover, if condition-based maintenance is deemed cost-effective, the supplier should identify subsystem parts or elements of the system that would benefit from remote monitoring. Additional resources, such as the challenges of condition-based maintenance, and using integrated logistic support to design for supportability can be found at the JETRO Project Consulting Group at www.jetroproject.com under the Download tab.